In the last lecture, we talked about a breakdown of how to think about thermal physics and how it connects to the various theories that we're going to study in this course. Today, we'll embark on the first one of those, classical thermodynamics. So this will be lecture 2 on what is classical thermodynamics. The thing I mainly want to emphasize today is that classical thermodynamics is a different type of theory than most of those you will have encountered if you've taken other undergraduate physics courses. Those other theories are of a type called dynamical theories. Now, dynamical theories, or I should say the term dynamical theory, encompasses all of the theories that you probably will have covered so far. So classical mechanics, E&M, quantum mechanics mostly. And so we should write down really concretely what constitutes a dynamical theory. So a dynamical theory involves a few core elements. First, it involves a space of states, possible states the system could be in. So we'll say a state space. It involves an initial condition telling us what state the system is in at the initial point in time. It involves a parameter that we call time over which the system evolves. And perhaps most importantly, it involves a rule that tells us what happens as the system evolves in time. The problem is that thermodynamics is not this type of theory. Now that may be a little bit confusing given that thermodynamics has dynamics in the name, but actually this is merely a historical accident. The first usage of this term was probably by Lord Kelvin, who was a physicist in the latter half of the 19th century, and I guess in the first part of the 19th century as well. He used it when commenting on the work of an earlier physicist named Sadi Carnot. Carnot's essay had been titled, in French, On the Motive Power of Fire. Motive power referring to the motive power that fire or heat gives to a thermodynamic engine. So because heat drives the engine, Kelvin translated that back to the Greek as thermodynamic, heat moving. Unfortunately, that name came to be applied to the whole theory, even though it's not a theory of dynamics. So it's just one of those things that we'll have to get over and carry on. In any case, thermodynamics is a type of theory called a control theory. A control theory has a few of the same aspects as a dynamical theory, but some which are different. So it also involves a state space. It also involves an initial condition that the system is in before we touch it. However, it doesn't need to have necessarily a time parameter. It does have a rule for evolution if there is no action by the user. But as I guess I'm hinting at, we also have the necessity of user action being included in the theory. That's why it's called a control theory. The user is doing some sort of control operation on it. So, in fact, one thing that we need is the set of allowable operations in every state. And then we also need the result of every one of the operations that we can do. So just to give a little visual for this, A dynamical theory might involve some different states. And we might find that time evolution causes us, if we start here, to go first here, and then here, and then here, and so on. And in particular, we would need a rule about where we go from every single one of these states. So for instance, we also need rules about things that the system doesn't even do. We need rules, for instance, for starting at this state as well. A control theory, on the other hand, might have the same states, but instead, given that we started this state, perhaps, it tells us where we can go. So perhaps there is a set of 3 allowable operations, one of which takes us here, one of which takes us here, and one of which takes us here. Notice also that control theory does not necessarily need to have any time parameter at all, whereas it still does share some of these features. If there is no time parameter, then the rule for time evolution with no user action is just that nothing happens. In any case, with these out of the way, let's give a couple of examples of each type. So over here, I'll work out examples for some dynamical theories. The first one is one that you're very familiar with, which is Newtonian mechanics. Now, what's the state space for Newtonian mechanics? Well, it's the set of positions and momenta. Let's say that we're talking about a single particle, and that particle is living in 3 dimensions. Or positions and velocity. So in that case, the state space looks like R3, Cartesian product R3. In other words, we need 3 parameters that are all real to specify the position, and 3 to specify the velocity. The initial condition will just be a single initial position and initial velocity. So this will be some element of this first state space. The time parameter is just a real parameter called time. So let me call it t here. Then the rule for time evolution is as follows. The trajectory that the particle takes will satisfy a given differential equation. And that differential equation is just d squared dt squared of the particle's trajectory over time. Let's call it x of t is equal to the force. Oh, and let's do some vector arrows just to be totally complete here. Is equal to the force, which might be dependent on both position and time. Oh, and I've forgotten mass. So let's divide by mass here. In any case, this is all of the parameters that we need. Let me work out one more example that's also somewhat interesting. So you wouldn't often think of this as a dynamical theory, but an integer sequence is another type of dynamical theory. Let's work out all the details. Just for concreteness, let's focus on the Fibonacci sequence. So here the state space is going to be the integers. Math bold Z. Good. The initial condition will be a set of 2 integers. So just to make sure that that fits what we were saying, let's actually say that the first one of those integers characterizes something about the rule, and we are just focused on the second one. So let's say it's an integer that we'll call b. The time parameter is now a discrete time parameter. It's not continuous like t was for Newtonian mechanics. Let's call it little n. And this is going to be an element of the natural numbers, since the Fibonacci sequence is typically only defined for n greater than or equal to 0. And the rule, finally, will be that if we call the sequence f of n plus 2 is equal to f of n plus 1 plus f sub n. Now, because we need to get that second initial condition in there, let's say that this sequence is given for a, where a is equal to f sub 0. So we're just indexing. So just to give a concrete example, say that a is equal to 2 and b is equal to 3. Then we get f0 is equal to 2. f1 is equal to 3. f2 is equal to 5. f3 is equal to 8, and so on. So theories of dynamics don't need to be in continuous time, and they don't need to be physical. They could be anything that fits this particular set of definitions, or I should say fits this one definition. Now let's talk about some examples of control theories. The first and maybe easiest example is another physical example. Let's think about a mass on a spring, but one which we're applying an external force to. Okay, so this thing has a state space that's now it's just one dimensional position and one dimensional in velocity space as well. So it'll just be r cross r. Its initial condition will just be, again, some initial position and initial velocity. Now, we do have a time parameter in this case, and that time parameter is continuous. And we have a rule for time evolution with no user action. And that rule in this case is, again, just m times the second derivative of x of t is equal to, well, now we have, if this has spring constant k, minus kx, but then plus whatever our external force is. So let's say that this depends on t, and that the user is getting to choose it. So now, what are the allowable user actions? Well, it's all the forces as a function of time. So the user effectively chooses this f of x of t function. And the result of the action? The result of choosing a particular function is that function is applied in this differential equation. So this is one example of a control theory. Another example of a control theory is playing a solitaire game. I should have labeled this, sorry, forced spring. So in any solitaire game that's deterministic, that has no element of randomness, well, we can talk about each of these aspects as well. The state space is the possible board states of the game. The initial condition is whatever the starting condition is for the game. The time parameter? Well, that's going to be the number of turns. So the user proceeds through turns. And usually in a solitaire game, the result of going through some number of turns is that you might lose the game if you go too long, or perhaps there's just some condition that it's not possible to escape from. Okay, what's the rule that governs what happens if the user does no action? Well, nothing happens. The game can't proceed. Or maybe we say the user automatically loses if they cease to take actions. I won't even put that up. The allowed operations are all of the moves that a player can do at that board state. So for instance, if we're playing the card game Solitaire and we're at a point where we have an ace down, maybe an ace of clubs, and a two of clubs exposed, then one possible move is now to move the two of clubs onto the ace of clubs. And finally, the result, well, I should say the result of each action, well, that's going to be dictated by the game, but it's in the game rules. Effectively, these are just rules of the game. And with that, I think that this is a pretty good survey of the kinds of things that we could see from both dynamical and control theories. Let me get the board cleaned up, and then we'll talk a little bit about how classical thermodynamics fits this model. Okay, our next order of business is to figure out how classical thermodynamics fits the model of control theory. All right, so what is the state space? Well, first of all, we said that classical thermodynamics in the last lecture is a theory in which we have a collection of isolated, simple systems. So the first thing is that the state space of that whole collection is just the Cartesian product of the state spaces of all of the subparts. I'm going to say the state space for a given simple system is called gamma. So we'll say that this is gamma 1 times gamma 2 times ... times gamma k if we have k simple systems. Now, what is the state space of each of these? Well, we'll get into that a little bit later in future lectures, but it's just going to be some subset of Rn. So what I'll say is that gamma j is just a subset of Rn. And it's important to note that n can actually be different for the different j's, but let's just write Rn for now. Now, what is the initial condition? Well, it's just given by what state each of the simple systems is in at the start, whenever we start sort of thinking about things. So initial state of each system. I'll say simple system. Awesome. Now, time parameter. This is very important. As I said, classical thermodynamics is not a theory of dynamics, and in particular, there is no time parameter here. The reason that there's no time parameter is that each of these systems is in equilibrium, which we'll talk a little bit more about in the next lecture. Next of all, we have our rule, which is also going to be trivial here because there's no time parameter, so there needs be no rule for no user action. Next, the set of allowed operations. To discuss this, I'm going to have to bring in a new notion, which is the notion of thermodynamic entropy. Thermodynamic entropy is going to be some function on the space of all possible states. So let me point out over here on the side, we now get entropy rearing its head for the first time. It's going to be a function which we call S, or sometimes STH to distinguish it from other notions of entropy, that goes from all of these states to the positive real numbers. The set of allowed operations is some subset of all of the operations, all of the moves that we could make in the state space that let the entropy increase or at least stay constant. So it's a subset of entropy non-decreasing moves. So for instance, if state 1 has an entropy of 1 in some system of units, and state 2 has an entropy of 2 in the same system of units, then it may be possible, though it is not necessarily possible, to move from the first to the second state. Lastly, the result of each operation is just that we end in that state that's allowed afterward. Now, can I be more specific about what this set of allowed operations is? The operations that in general we'll call control operations. And without getting a little bit more into the formalism, I can be at least a little bit more specific. There are two types of control operations in classical thermodynamics. The first we call an adiabatic work operation. An adiabatic work operation is one that leaves the entropy constant. It's called adiabatic, which more or less means done quite slowly, because typically the way that we achieve these operations or approximate these operations in real life is to change the parameters of a system very, very slowly, such that it equilibrates in a way that doesn't change the entropy at each point in time. The second type of operation is one that I'm calling joins. Now, credit where credit is due. This is a term from a paper by Ingvason and Lieb from the 90s, and they in fact use joins to mean something slightly different. I've appropriated the meaning here. This is also a good point to note that this control theory formalism here is from a 2014 paper by the philosopher David Wallace called Control Theory, or Thermodynamics as Control Theory, which I highly recommend to even interested non-experts. Aside over, so back to this. So join operations are different from adiabatic work operations in that they usually increase the entropy. What happens is that you have your whole state space, and the join operation causes the system to become restricted to a smaller subspace. What happens, the result of this particular operation, is that the system ends up in the state in this subspace which has the highest entropy. So if we look at all of the points, we choose the one that has the very highest entropy. And that is where the system ends up. Oops. We'll get more into types of joins in later lectures. But this is how thermodynamics, classical thermodynamics, fits the definition of a control theory better than the definition of a dynamical theory. Now, just to editorialize a little bit before I end this lecture, I think that this is a very important point to get across. Because we've had so much work done with dynamical theories up to this point in a typical undergraduate career that I think shifting perspective can be very challenging. But I think you should take it as a sort of invitation. This is a new type of thing that you get to do in a physics class that uses much of the same formalism that you'll be familiar with. We'll get to use lots of math. We get to do lots of things involving physically relevant systems, but in a slightly new sort of environment. And so I think it's very important to sort of shift focus, shift perspective, and think about control theories and user action being a core part of what we're talking about here. And with that, I'll say thank you so much, and I'll see you in the next one. Bye-bye.